So last week we look at the serviceability limited, how to do the design checks, for serviceability limited. So technically we look at the crackings and deflection. So the crackings and deflection have couple of different methods. So for example, deflection, you can do it using simplified method or deemed to confirm method. Similarly, crackings for members within the enclosed area or interior members, interior environmental condition. So then you may able to do it by checking the spacings for all members, including the interior or exterior environmental condition. You should be able to check the cracking requirements using two methods. Direct method, that means technically you will calculate the crack width. The other one is indirect method. That's technically you will look at the stress in the steel. You will look at the stress in the steel and compare that one with the allowable stress given in the table. Okay, so that's the two methods. You should be able to do using both methods. Okay, that means you should be able to calculate the stress in the steel, and then you also can check the crack width. Okay, so the tutorial questions deal with both and shows step-by-step calculations. Sorry. So if you have any problems, you can ask and we will discuss those aspects in the tutorial, but as you know that each question will take half an hour or more. Okay, each of the questions sometimes take more than half an hour, so it is not possible to work out each and every question step by step, but we will look at main step and we have to get the numbers, and you should be able to put it in the equations and check that with the given solutions. Okay, I strongly recommend you to read the standards in the slides and work by yourself. Okay, so reading solutions will help only if you work out by yourself. Just reading that like notes or stories will not help, because when you take pen and paper, then only you will understand actually what happened. Okay, so today we will look at the ultimate limit state. So when you do the design of concrete, so we talk about the concrete beam, you should make sure, or you should ensure the beam will satisfy or comply with both ultimate limit state and serviceability limit state requirements. Okay, we started with the serviceability limit state because if you don't know the dimension of the beams, okay, if the beam dimensions are known, okay, So for example, you are checking some existing structures, so the beam structure, beam dimensions are known, so you should be able to start from either ultimate or serviceability, no problem. But if you don't know the dimensions, okay, depth of the beam, then you should be able to, or you should start with a deflection check, so that your assumed depth can be verified whether it complies with the deflection requirements. Okay, so that's why we started with the serviceability limit state. So when you look at the ultimate limit state technically deal with the rupture or collapse of the building or member. Okay, so if the condition, if you don't use the microphone, please mute it. Yeah, sometimes. Okay, so if you have some checks, a bending or shear, then if your beam or if your design does not comply the requirement, technically the beam will fail in bending or shear. Okay, so that comes under the collapse of the structural member, and that also may need to collapse of the structure sometimes, or the structure become vulnerable for the given loadings. So this is quite critical. So we use different load cases. So in this unit, as I told, we don't deal with the wind, earthquake or snow. So we only deal with the live load and dead loads, because the wind load is quite lengthy. You know, wind load calculation is quite complicated. So that's normally covered in the steel unit ENEC 20002. So we are looking live load and dead loads only in this unit. In that case, ultimate limit state will have 1.2 G plus 1.5 Q. Okay, so that's important for ultimate. For serviceable, different. For ultimate limit state, the load, design load FD is equal to 1.2 G plus 1.5 Q. So G is the dead load, Q is the live load. So you need to make sure you are using correct load combination. If we use wrong load combination, you will not get marks, because your design does not comply. So the question here is whether your design is comply or not comply. Okay, there's no in between. Okay, so you just make sure when you submit the design, the assignment 1, use correct load combination. For serviceability, we have to use serviceability state load combination. If you look at the workings, tutorial workings, we use G plus Q or G plus short term Q or G plus long term Q, something like that. Okay, so here the worst case is 1.2 G plus 1.5 Q. If you have wind, we have other load cases as well, but we don't have the wind load in this unit. So for ultimate limit state, so if you are doing checks What are the checks will come? Bending, shear, axial force. This is for columns. Okay. So anything, if you are calculating bending moment, shear force, axial force, this is the load combination. Okay, so you should know what is G, what is Q, that is dead load and live load. So for the loads will be in kilonewton per meter, G, Q, FD, everything will be kilonewton per meter UDL. So that is the beams, it can be continuous beam or whatever. UDLs. For slab, that's we will discuss next week. So that is pressure. So G, Q, F, D, everything will be kilopascal. So that means kilonewton per meter square. So that unit is important. Unit is important, and you should know what to do. Okay. So we work out this one. Shortly. So if you know the FD, to check the bending, shear and axial force design, what we need the bending moment diagram. We also need the shear force diagram and axial force diagram later. Okay. So if you are looking the beam slab, okay, we'll come to the column a little bit later. So if you want to design beam or slab, we need the bending and shear force diagrams. How to draw the bending and shear force diagrams? Because if you don't know the bending moment diagram or shear force diagram, you cannot design. Because, you know, for ultimate limit state, the condition is something like that. So this is the criteria. R star is the demand, and this is the capacity, design capacity. So in this class we will learn how to get this one, how to get the design capacity. Okay, how to get the design capacity. So if you have the design, if you have the design capacity to check this condition, you also need the demand. Okay, so what is the demand? So that means if it is a bending moment, maximum bending. If it is a shear, maximum shear force. So we need to know what is the maximum bending moment in the beam, what is the maximum shear force in the beam. Okay, so generally if you have, say, your project, something like that, isn't it? The project or any slab system like that. So let's say you need to look at the beams. So we have one beam, another beam, yeah. So we have 1, 2, 3, 4 beams this side, 4 beam this side. So how to get the maximum bending moment for each of these beams? That's the first question. If I know the maximum bending moment, then only we can do some checks, yeah, or maximum shear force. The R can be anything. So this is a maximum demand. So maximum bending moment, maximum shear force, maximum axial force, whatever. So we need to know what is the maximum bending moment. So for that, what we need the bending moment diagram. We need bending moment diagram or shear force diagram. Then only you can get the maximum values, then you can design for that. Okay, so if I look at this beam, okay, generally we have a slab system. So your 4 beams, 1, 2, 3, 4 will go like this. Okay, and also we have the beams other side as well. So if you look at the 3D view, something like that. Okay, so you'll have beams will go this way and this way. Yeah, so if you look at this beam, that is this one. So for the beams, normally the loads comes from, so we have the beams this way and here as well. So for this beam, the loads come from this slab and this slab. Yeah, so it comes from both sides. So how these loads will distributed, we will, I think there is a slide in the last week, the load estimation or something. In that slides, the last slide shows how the load will be distributed. So if you look at a slab, supported by 4 sides, 4 sides is called two-way slab. So the load in this slab will go to this beam, this beam, this beam and this beam. Okay, so how much will go here, how much will go here? So we need to find it. So what we do is we will draw a 45-degree line. So this is 45 degree. Okay, the line is 45 degree. each lines. So we'll have something like this. It's depend on the dimensions. So if it is lengthy, it will come some. So it's a trapezoidal side. So this area, whatever the loads in this one will go here, and whatever this triangle will go here. So what will happen? This beam will get a trapezoidal load from the slab. Yeah, this beam will have a triangle distribution. Okay, so from this side we have a trapezoidal distribution, from this side. So both sides will have a trapezoid. For this one, you'll get a triangle. Okay, so whatever the load in this area will come to this beam. Okay, yeah. I haven't get the bending moment diagram yet, but we need the bending moment diagram. That's why we are looking how to find out the loads. So for the slab loading, technically self weight of the slab superimpose dead load, live loads. These are the loads in the slab. Will transfer to beam. Okay. Dead load from the slab, live load from slab. Okay, so what will happen? This one can be trapezoidal shape or triangle shape or uniform one, rectangle distribution. So we can have either trapezoidal, something like this. If you have two-way slab, yeah, it can be a triangle. Or if you have a one-way slab means it is only supported two sides here and there. It is only supported two sides. It is one-way slab. So the load will, half the load will transfer here, half the load will transfer here. So the load distribution will be a uniform distribution because it's a one-way slab. If it is a one-way slab, it's a rectangular shape distribution. If it is two-way slab, if it is this beam, it's a triangle distribution. If it is this beam, trapezoidal shape. So we may have three different possibilities for the load distribution. You get it? Yeah. So the beam can be either one way or two way. There's no other ways. Okay. The beam can be either one way or two way. So depend on that. If you consider one beam, the load distribution can be either trapezoidal shape or rectangular shape, triangle shape or rectangular shape. Okay, it's depend on which beam you are considering. Any questions so far? Yeah. So then we know the loads. So we know now we know the load from slab to beam. Okay. So we have do it separately in the assignment. Dead load from the slab, live load from the slab. Okay. So the distribution is either so now if we want to use this load combination, load distribution, the first two cases are quite complicated. First two cases are quite complicated because they have trapezoidal or triangle shapes. Normally in our undergraduate structural analysis we use with the uniformly distributed load like this one. Yeah, this is easy, but these are too complicated distribution. And in AS3600 clause number 6.10 explain how to get the bending moment and shear force diagrams, using simplified So they explain how to get the bending moment and shear force diagrams using simplified analysis. So if I want to get the bending moment and shear force diagrams for the beams, I should be able to use this one. I should be able to use that one. So if you want to get the simplified method approach, if you want to use it, then what you need to do is you need to look at the clause number 6.10. If you read the clause number 6.10, then you will find there is a requirement. Says the load should be uniformly distributed. So they said the load should be uniformly distributed. What does that mean? Only uniformly distributed load, only uniformly distributed loads can be used this simplified approach given in the 6.10. So if I want to use clause 6.10, I need the uniformly distributed load. This is okay because that is uniformly distributed, but these two are not okay because those are not uniform. So one is triangle distribution, other one is trapezoidal. So I need to get a uniform distribution. So what they do is, before we go into the 6.10 section, we look at the trapezoidal distributions. So what we do is, we will find out an equivalent load that is distributed uniformly. So we'll say the equivalent load. So instead of this trapezoidal distribution, you should look at the equivalent load. So we need to find, instead of this one, we have to use this one so that we can use 6.10. Similarly, for the triangle distribution, they will find equivalent loads. There is an equation in the week 2. If you look at the week 2 slides, week 1 supplementary, if you go to that one, this is, if you look at that, okay, so this is not your unit, it is for the another unit, but I just give that one as a supplementary. So this is we discussed. So these are the things we use for the undergraduate, okay? So if you want, you can look at those things. So this is the distribution. We have equal loads. So this one, the trapezoidal distribution and rectangular distribution will have a uniform distribution. So here the maximum is W Lx by 2. W is this one, Lx is the smallest, this one. So this is the maximum, but so it's varying from 0 to maximum. But here is not Lx by 2, Lx by 3, 1/3. But it is from here to there same. Similarly, so here we have quite different distribution. So rather than that one. So when you calculate the loads, you need to calculate equivalent uniformly distributed loads. So it is better show both diagrams and calculate the right side ones. Okay, for your project also you need that one, because you need to design one of the beam. Yeah. So what you need is, we have the right side. What you need is the right side load distribution for all the beams. Is it clear? Okay. So once you have that one, and you can use Any questions?
This is really the bad habit. So this is my thought. If you actually see just characters in like the past few months, but this process of progress now.
Sorry, there is some voice. Is it question or you are talking with someone else? Hello, so there's some noise comes. Could you please mute your phone if you are not talking to me or it's about, okay? Yes, it's recording.
So this is my own rat bot. You can actually see which senior they purchased in like the past few months, but this bot was right. So like there's people like spent like millions of dollars on this
So you can mute the guy. His mic is turned on.
So he is talking to me or not? No.
No, sir, he's not talking to you.
Okay. I will mute him. Give me a second.
You can mute, sir. You can mute Pi for Pi.
Okay. Okay. Sorry, there's some. Okay, so don't turn on the mic because it's otherwise I need to jump in and it's lots of time. Okay, so now you have the uniformly distributed loads from the slab. Yeah. So now UDL from slab for beams, you also need to add self weight of the beam. So when you have the dead loads from the slab, when you need to add the self weight of the beam, because that is not included earlier, it's only slab weight is included, so we need to add the self weight of the beam. Okay, so you need to add the self weight of the beam. The life load from the slab comes as it is because there is no additional life load for the beam. So now we have total dead load and live loads. So then you should be able to calculate FD as a 1.2 G plus 1.5 Q. So technically Q is this one. The dead load is the total. Come here. Okay, so the unit will be kilonewton per meter. So if you have any problem, you should ask me. If you don't know, or if it's not clear how to get this one, please let me know. Okay, if you have, I think there is a worked example in the same slides, finding loads and distributed loads. So remember, that is very fundamental calculations that's given for the associate degree students. Okay, so I don't put lots of complicated calculation in the slides. So that slide was prepared for the associate degree, very fundamental how to get the loads, and they are very first, it's below the bachelor degree level. Okay, so if you have any problems, feel free to ask me how to get that one, and we will also discuss the tutorial class, and also it's important for the project, so we also can discuss at 4 o'clock tomorrow, or every Tuesday 4 o'clock, sorry 5 o'clock, sorry 5 o'clock Queensland time, 6 o'clock Melbourne time. Okay, so we have the loads, then 6.10, I will explain that one tomorrow. Will tell you how to draw the bending moment diagram. So if you're looking this beam, 1, 2, 3, 4 columns, because each one is column. Yeah. So 1, 2, 3, 4 columns. So technically, if you look at that beams, you have a column, second column, so if you're looking at the beam from the side, it looks like this. So for each beams, we have the uniformly distributed loads. We have the uniformly distributed load. Yeah, you should be able to calculate. Then you should be able to draw the bending moment diagram. Do you need to explain that one? I have a separate video. Do you want put that one here? How to draw the bending moment diagram, or you should be able to read clause 6.10 and able to get that one? What's your preference? Do you want that separate explanation? Not. Yeah, I'm not going to do it now because it will another 30 minutes work. So what I will do is I have separate video. Okay, so I will put it there. So I will put that as a simplified method. So I will explain how to get that one. Okay, so that's not belongs to this unit. So don't confuse. What is this? He's talking something new things. It is belongs to that other units. So I will put that video. So that will explain how to draw the bending moment diagram or shear force diagram. So now the bending moment diagram and shear force diagrams are known. I put a separate video, those who need extra help. Otherwise you can read clause 6.10 and able to get it. So I will put separate video how to read or how to interpret the clause 6.10. So okay, so don't worry, that is a separate video because today we will discuss about the design part. So now I assume you have a beam. You have a beam with some loads. So you should be able to draw bending moment and shear force diagram. You should be able to draw bending moment and shear force diagram. So if you know how to draw the bending moment and shear force diagram, technically you should be able to get the maximum bend. Yeah, you should be able to get the maximum bend. Similarly, maximum shear force. So today we will see how to find out required reinforcement. Because if you have, say, if you have a beam, just consider simply supported beam. So the bending moment diagram is like this. Yeah, isn't it? For the loads, maximum is WL squared by 8. Is that correct? So the beam will bend like this. So the bottom part will be under tension, top part will be under compression. Yeah. So the concrete cannot take tension, so then the cracks will develop. Yeah. So we need to provide some reinforcement. Steel reinforcement will be provided so that you take the tensile force while compression will be taken by concrete. So we need to know how much steel we require. How much steel we will require. So my purpose, the first one is find out the amount of steel that required so that the beam will be safe under the given bending moment, maximum bending moment. Okay, so for that we will use section 8. Under that one they have some assumption. This is the first one. Under the bending, the plane section remain plain. So that means under the strength of material in your undergraduate you learn this one. The plane section remain plain. What does that mean? Plane section remain plain. If you have a beam, so if you look at one plane, if you cut here, this is a plane, isn't it? The beam, cross section. Yeah, so this is a plane. Actually it looks like a rectangular cross section. Okay, so when it is bends, this cross section remain as plane, so it will still a straight line. Okay, so even if you cut it here, it is still rectangle. Okay, so the rectangular section, if you have a cross section, it remain as a rectangle, it doesn't change. Okay, so if you put a color there, it will remain in the same line. So that is the first assumption. That is a basic assumption for the pure bending in the strength of material. So that is the first assumption, so that technically true. And then we also have some additional things. The last one is the bonding between steel and concrete is perfect. What does that mean? When you put the steel, the concrete and the steel have a bonding. So if you have a steel, it's keep that one. When you pull that one, it cannot come out. Okay, so the bonding is a perfect bonding. So technically, the bonding strength is much higher than the failure load. So the bonding between steel and concrete is perfect, so there is no separation. Okay, so you can assume that one. The second things are more important. For ultimate limit states, we assume there is no tensile strength. Remember, in the serviceability, we assume for crack section and uncracked section, in both cases, we assume the concrete is elastic behavior. Yeah, this concrete have elastic behavior, so that can take little bit of tension, okay, in the service. But in ultimate, there is no tensile strength. So tensile strength of the concrete is assumed as 0 under ultimate case. So the concrete cannot take any tensile force, only compression. Concrete can take only compression. All the tensile forces should be taken by steel. Okay, so at ultimate, that means just before the breakage. Okay, at ultimate, we also assume the steel reach the yielding point. Steel reach the yielding point, and the concrete compression, the strain should not exceed 0.003. So the maximum compression strain, the concrete is 0.003. So these are 3 assumptions. So concrete important. The steel reach the yielding point. That means if you look at the steel stress strain relationship, this is for steel. Okay, how the stress strain relationship? First, elastic. Yeah, this is elastic region. Then how this point is called? End of the elastic. How to call this one? Yielding stress. Yeah. So for steel, that is FSY. Fs is the steel stress. FSY, steel yielding stress. For N-type bars, FSY is equal to 500 MPa. FSY is equal to 500 MPa. So this is yielding strain. Sy strain. This is yielding stress Fsy. Fs means stress of the steel. Fsy is the yielding stress of the steel. Okay. So after that, in real case it is going like this. Okay, but the standard assume here something like this, a perfect plastic. So there is no increase in the stress of the steel after the yielding point. After the yielding point, the stress will not increase in the steel. So what does that mean? Initially it will increase. Once it reaches the yielding point, it will expand without any additional force. So the longer the length is, so somewhere here this will break. Okay, that is a fraction. In real life it's actually something like this. The fraction might be here. Okay, so if it is longer, if the failure is somewhere here, or sometimes it may be somewhere here. So which one is better, here or there? Whether you want to have this one is longer or shorter. Shorter. They need longer one because this is called ductility. Okay, so the longer the post yielding strain is, have more ductile property. Okay, for ceramics, sudden failure, brittle. If this one is short, that is brittle material. Okay, concrete, plain concrete is a brittle material. Sudden failure. Steel, if it is a high carbon steel, it will be brittle. Okay, but for this reinforced concrete bars normally have good ductility. So we need good ductility so that we know the beam is reached the yielding point, is expanding. So that's quite danger if it is expand too much, because it will fail. So we like to have the design somewhere within this region. Okay, not here. So the third assumption is steel in the ultimate case. Remember, this is ultimate case. Okay, very large extreme load, 1.2 G plus 1.5 Q. So under the extreme loadings, we assume no tensile strength concrete strain cannot exceed 0.003. If it is exceed, it will fail in compression. Okay, the other one is steel has passed the yielding point. This is here. Why? We need to make sure they reach the yielding point so that we'll have enough warning, because in this region steel will expand without any additional force. So if it is already past the yielding point, we will have some kind of warnings. X very large deflection or something will show us that's reached something bad. So these are the three assumptions we need to remember. Okay, we need to remember means I will not ask what are the assumptions, okay, but you need to know. So these are the two things. Under the bendings, we need to make sure we need to satisfy both ultimate and serviceability cases. Last week we discussed about the deflection and crack control requirements. Now we need to make sure we're being comply with the fractional strength and shear strength requirements. Okay, then we can discuss about the detailings. So this is the concrete and steel stress strain relationship we'll assume or we'll consider in our design. So we discussed this one. So after the yielding, you can see that is technically no increase in the strain, increase in the stress. Sorry, I think this comes in the wrong order. Okay. So now we will see how to calculate the capacity, because we know how to get the maximum bending moment. So we need to know how to calculate the maximum capacity, the bending capacity of the concrete beam with the reinforcement, so that we can see how much steel we need, because if you increase the steel, the capacity will increase. So let's assume we have a beam with the reinforcement at the bottom side. Bottom is the tension, top is the compression. So it is not always at the bottom, okay? In some cases the top also will come under tension, bottom will be compression. We will discuss normally in the tutorial class. So technically one side is under tension, other side is under compression. So in this drawing, the tensile side is shown as bottom part. So when you have the tension on the bottom, what we'll do, you need to provide some steel. So I provide some steel bars. I don't know how much that one. So I put the area of the steel bars as AST. A area, S for steel, T for tension. Okay. AST, A for area, S for steel, T for tension. So this is tensile reinforcement. This is tensile reinforcement. That's what we call AST. So I provide some steel. At the moment I don't know how much I need to provide. So I will put some steel. We'll see how much the bending capacity will be. So when you calculate this capacity, there's some standard terminologies. So capital D is the overall depth of the beam from the top to the bottom. So that means top means compression zone, from the top of the compression part to the bottom of the tensile zone. That is capital D. That is called overall depth. Overall depth. Small d is the effective depth, that is the distance from the compression zone, the extreme fiber of the compression zone, to the centroid of the tensile zone, to the centroid of the tensile zone. So small d, the b is the width of the beam. So this is the standard notation. You should know what is d means, what is d means, what is b means, and also AST. So if you have these ones, then we need to calculate the moment. How much moment it can carry without failure or before failure. So I apply the bending moment, and bring to the failure stage, almost near to the failure. Almost near to the failure. It's not failed yet, but it's going to fail. So this is the maximum. After that it will fail. So I applied a moment slowly and increase up to the maximum. So that is the ultimate moment. Ultimate moment is mu. So that is the moment I applied at the moment. So when you apply the moment, the bottom part will be under tension, top part will be under compression. So there will be a strain distribution. There will be a strain distribution that is shown in the first diagram, strain distribution. So according to the strength of material theory, the strain distribution is a straight line from like that. So we'll have two triangles. Where the strain is zero, we call as a neutral axis. We call as a neutral axis. So if you remember the last week lectures, we calculated depth of the neutral axis, y bar. Yeah, the y bar for crack section and uncracked section. We calculated the depth of the neutral axis. But remember, that is for serviceability limit state. We assume the concrete beam behave as elastic material. But here it is not elastic material. It's past the yielding points. It's almost near to failure. Okay, it is near to failure. So if you look at that one, elastic means the straight line. Okay, so it's reached, it goes up, and it comes to the fractional. Okay, so it is quite different. So that calculation and this calculation is different. Okay, everything is called neutral axis, but that neutral axis is for elastic behavior, but this neutral axis is plastic. Okay, it past the yielding point, is just before the ultimate failure. So the definition for neutral axis is said strain is equal to zero, or stress is equal to zero. So where the strain is equal to zero, that is called neutral axis. That's what I put as a blue dotted lines, horizontal line. So that is the neutral axis. So the depth of the neutral axis from the compression zone is marked as a dn. dn is the depth of the neutral axis in the moment calculation. So last week we calculated two depth of the neutral axis. One is for cracked section, another one is uncracked section. So that is completely different. Don't confuse. That is depth of the neutral axis for elastic materials. Okay. So in that one, the concrete is assumed to be the elastic material under service load. This is under ultimate load. the load is much higher, so it is not within the elastic limit, so we cannot use any of the theories we learned last week. So the depth of the neutral axis is marked as a dn, which I don't know. Okay, so I know capital D, small d, b. The dimensions are known. I don't know how much AST I need. Okay, the area of reinforcement I don't know. Okay, I need to calculate. So I don't know the AST. Now I have another term called depth of the neutral axis, dn. So I have two unknowns now. Okay, so far we had two unknowns. I don't know dn and I don't know the AST, area of steel required to carry the maximum moment. Two unknowns. So in the ultimate case, I put the strain on the top, that is under compression, the strain and in the top fiber as 0.003, because that is the maximum strain the concrete can carry. That is an assumption. Okay, so the standard says the strain in the concrete cannot exceed 0.003. If you exceed, the concrete will fail under compression. So that's what standard says. So I take the extreme case, that is just before the failure. So I said, okay, that is reach 0.003. Okay, so I put that one 0.003. So if we know that one, there are two similar triangles, the green color on the top, the red color in the bottom, both are similar triangles. Yeah, so using similar triangle theory, you should be able to calculate the strain in the steel. I put as a EST. So epsilon ST, yeah, you should be able to calculate using similar triangle. So now you know the strain. Generally, if you look at the strain in the steel, that will be larger than the yielding strain, and that is one of the assumptions. So we need to make sure that reach the yielding point. So then if you have strain distribution, then we should be able to get the stress distribution. The concrete stress distribution is a parabola under compression. That I draw. Under tension, we said there is no tensile strength. So there is no stress distribution. There is no stress distribution below the neutral axis for concrete. Below the neutral axis, okay. Give me a second. Can you see? So below the neutral axis, you don't have any strain in the concrete, but the steel can take the tensile force, so there will be a stress in the steel, that is tensile stress in the steel, and the compression stress in the concrete is something like that. It's a parabola. Okay, so the problem with the parabola is, if we need to find out the total force, I need to find out the area here. It's quite difficult. Finding area here is quite complicated. So the close 8.1 the close 8.1 said, okay, don't worry about this parabola. We will approximate this one. So can't be. Okay. we will approximate this one with like this. So what we'll do is we will draw equivalent area. So this is called approximate rectangle for concrete stress. So we don't need to worry about this distribution. We need to calculate this distribution here. So when you do this approximation, when they do that approximation, they said the stress here should be alpha 2 times f dash c. The depth is gamma dn. Dn is the depth of the neutral axis, which I don't know yet. So they put this depth of this approximate rectangle as gamma dn. So gamma and alpha 2 are given in the standard. The values are given in the clause 8.1. If you look at the clause 8.1, you should be able to see the equation for alpha 2 as this one, gamma as this one. Remember, these two values are larger than 0.67. Okay, so now we have a stress distribution. If you have stress distribution here, we'll have a force. Here we have steel to take the tension, concrete will take compression. So then we should be able to calculate the bending moment. Okay, I'll show that one, what to do actually. So when you have beam, so the neutral axis is somewhere here, I don't know where it is. Okay, the neutral axis I don't know. This is B, and that is capital D, and the steel is here. So that is small d. This is AST. So if you have something like this, the strain distribution will be like this. So this is 0.003, this is dn, and the strain here is marked like this. If you want, you should be able to calculate the strain using similar triangle. So this one, similar triangle, this one, divide by this, the ratio between this and this and this should be equal to the ratio between this and this. So Cu upon dn, the ratio between this and this equal to this, and this one from here to there, small d, so d minus dn. So this one is known. This one is known, yeah, that is 0.003. D is known, the depth of the effective depth of the beam, you should be able to find, yeah. So if you know the dn, depth of the neutral axis, which I don't have at the moment, if you know the dn, you should be able to calculate the strain in the steel. Okay, the strain in the steel. So the EST, sorry, the epsilon ST, the strain in the steel should be larger than yielding strain. Should be larger than yielding strain. Okay, that is the requirement. That is the requirement. What is the yielding strength for N-type? N-type pass. FSY yielding stress is 500 MPa. E value 200 gigapascal. Can someone tell what is the yielding strain? This is elastic.
That is 5,000.
Ah,
500 MPa, sir.
500 MPa is
Maximum.
the yielding stress. Yeah, I'm asking yielding strain. So that is here. So this is 500. I'm asking this value. The slope is the E value, isn't it? Young's modulus. Young's modulus according to Hooke's law. According to Hooke's law in the elastic region, E is equal to strain divided by stress, isn't it? Sorry, stress divided by stress is equal to, have you studied this one? Hooke's law. So the stress is 500, E is 200. What is the strain?
0.002. 0025.
0.25. So we should have, when you calculate, we should be larger than 0.0025. Okay, so we will see that one later, but you should be able to calculate using similar trial. So if you have the strain distribution like that, the stress distribution, approximate rectangular stress distribution is look like this. So we have a compressive force, FC, we have a tensile force FST. So this is alpha to F dash C, this is gamma dN. This is standard size. So the stress, uniform stress of this one. So if you have something like that, FC, the force, if you have uniform stress, force is equal to stress time. If you have uniform stress, stress time area. Area is the concrete area. If you look at this one, so this uniform stress is acting over this area. This one is gamma dN. This uniform stress, is acting in this area. The depth is gamma dN with this B. So area is equal to B times gamma dN. So this is FC. This is FC. FST, this force in the steel. So this reached the yielding point. So after that, stress will not change. Stress will be this much. So stress times area. Stress time area. Area is AST. So we have two forces here and there. We have two forces. One is in compression, that's from concrete. Other one is in tension, that's from the steel. We have two forces. We can write the expression like this. What is unknowns? I don't know this value, and I don't know this value. All other values I should be able to calculate. Alpha 2 is given in the standard. Alpha 2 is given in the standard. Yeah. Alpha 2 is given in the standard. Gamma is given in the standard. We look at in the previous slide. B, F dash E, everything is dimensions and the concrete strength. You should know. This is 500. So we had two unknowns. So to solve this one, we should write two equations. Yeah, we should write two equations because two unknowns. So to solve this one, if you look at this diagram is under equilibrium. The beam is under equilibrium. So this is equal to this one. That is the first equation. Fc is equal to Fst because the beam is under equilibrium. So alpha 2 F dash C B gamma dn AST FSY. So this is the steel force, this is the concrete force, both should be equal. So that is first equation. The second equation, so we got all these stresses because we apply a moment mu that gives this strain distribution and others. So this moment is applied, this is external moment, bending moment. So that should be balanced by these forces. So this one, we had two parallel forces. We had two parallel forces. FC, FST, both are equal, and this is Z. So two parallel forces acting in opposite direction will give a moment. That M is equal to how much? One of the force times distance. So FST times Z or FC times Z, both are same. FC times Z or FST times Z, both are same, yeah? Because FC is equal to FST. Okay? So this is the second equation. So this one is AST FSY, the Z, the distance. So this is a rectangular distribution. So the force will be in the middle. So this is gamma dn. This is gamma dn. So the half, this is gamma dn by 2. Yeah, half of that. So we have half of that, and from here to there is a small d minus half of the gamma dn. So small d minus half of the so we had two equations we should be able to solve because we are unknown. So where to get the mu? This is the maximum moment, and our calculation says, the standard says, this is our condition. Okay, if you want to satisfy the limit state, m star, the maximum bending moment from the bending moment diagram, should be less than or equal to pi mu. So the pi value is 0.85 for bending. It is given in the table 3.4 or I think 3.4. Double check that one. It's a 3.4 or 3.2. I think 3.4. Yes, 3.4. If anyone have the AS 3600, look at that one. Table 3.4 gives the pi value, strength reduction factor or capacity reduction factors. So this one from bending moment diagram. Yeah. So you should be able to get the mu value. What is the mu value you need? How much capacity you need? Yeah. So you can substitute. You know that value. This mu is here. So you know what is the mu at least you need, the minimum mu you need. All the values except AST and gamma DNs are there. You should be able to solve these two equations. You will get the second order equation and you should be able to solve them. Okay. So there is, once you have solved for DN and AST, and once you solve the equations, you will get the AST and DN. You need to check the DN value, whether the DN is less than 0.36 D. Okay. So they said, in the books they said Ku, it is dN upon D should be less than 0.36. This is for ductility requirements. Okay, this is for ductility requirements. This is for the ductility requirements of the beam. The standard says dN upon D should be less than 0.36. So you solve for DN and AST and check whether that is less than 0.36. So if you provide too much steel, you will exceed this one. So then you need to reduce it. Okay. Okay. So the standard says there are three terminology: under reinforced, over reinforced, balance section. So we look at this one. Oops. So the strain on the compression side is 0.003. Okay, the strain here, what is the maximum? 0.003. Okay, so this is the neutral axis where the strain is 0. So this is strain distribution, and when it is reached to 0.0025, the steel will get yielding point. Okay, 0.0025 is the yielding strain for the N-type bars. Someone already calculated, isn't it? So 0.0025 is the yielding strain for the steel. 0.003 is the maximum compression for concrete, that is in the top. So when you increase the bending moment, okay, so initially the beam is sitting, okay, initially the beam is sitting like this, horizontally. Yeah, so there is no strain here, there is no strain in the reinforcement. So everything is neutral, 0. Yeah. So then you apply the bending moment. So it's tried to bend. So what will happen here? Compression, here tension, both will increase. Yeah, here the compression strain will increase. Yes, it's under compression. This part under tension. So tensile strain will increase. So both will increase as you increase the bending moment. Okay, you slowly increase the bending moment. You slowly increase the bending moment. Both strains, this one and this one, will slowly increase. Okay, if the steel reach the yielding point at the same time the concrete reach the maximum strain of 0.003, if both happen at the same time, okay, when you increase the bending moment, both strains will increase slowly. Okay, depend on the area of the steel and the depth of the neutral axis, the rate of increase might change. So if both strains reach at the same times, that is called balance section. So steel yield at just at the time of the concrete reach the ultimate strain of 0.003, same time. If you look at the Ku value, that is the ratio between this one and the whole things, that is a dn, depth of the neutral axis, using similar triangles. If you look at this one, those who are interested, you can try. This is 0.003, this is 0.0025, this is dn, and this is d. So if you calculate the dn, similar triangle, 0.003 upon dn equal to this one, d minus dn. If you calculate the dn, how to solve this one? You can cross this one, otherwise you can add the top and bottom. 0.0055 divided by, if you add bottom, it is d. So if you look at these two, this is maths, okay, you can add top and bottom. So if you look at these two, dn will go there. So dn upon d is equal to 0.003. If you work out, you will get 545. Okay, so the dn is equal to 0.545 d. So if you have this much of depth of neutral axis, the concrete will reach at the same time the steel reach the yielding point. So this is called balance section. Okay, this is called balance section. If the concrete reach the maximum strain, the maximum strain before this one reach the yielding, that is called over reinforced section. If this one reach, the concrete reach the 0.003 first, that is called over reinforced section. If the steel reach the yielding point first, that is called under-reinforced section. Okay, so that is what is explained here. If the steel yield before concrete reached the 0.003, that is called under-reinforced section. If the concrete reaches ultimate strain 0.003 before steel reach, that is over-reinforced. So if you have an over-reinforced section, the next, because concrete reached the maximum, so what will happen if you increase further? Concrete will fail in compression. So the concrete failures are very brittle. We don't like that one. So over-reinforced sections are not good, not recommended. So over-reinforced sections are not good. So we like to have our design as an under-reinforced section. That means Ku should be less than 0.545. We shouldn't exceed that one at any cost. So we shouldn't have over-reinforced section. It's very bad. Balance also not very good because we don't know which one will fail. So under-reinforced section, Ku should be 0.545 or less. But remember, this is for under-reinforced section. But the standard already said you should have less than 0.36. That is for ductility. So over-reinforced section limit is 0.545. The ductility limit is 0.36. So if you satisfy 0.36, it is already over-reinforced, because anything below 0.545 is anything below 0.545 is under-reinforced. So if you satisfy this one, it also satisfy under-reinforced condition. Okay, so under-reinforced section will be satisfied with this ductility requirement as well. Okay, because for under-reinforced it should be less than 0.545. So if it is less than 0.36, it's already less than 0.545. So it's already under-reinforced section. So that both will satisfy. So all our design should satisfy 0.36. Okay, so this is called under-reinforced, balance, over-reinforced. So we would like to have everything under-reinforced, but remember, for the ductility we have further down. The ductility requirements are set by standards. This over-reinforced, balance, these ones are set based on the strain values. Okay, the reason I am telling the ductility requirements has been changed in 2009. AS3600 revised every 10 to 12 years. Okay, current one is 2018. The previous one is 2009. Okay, so 2009, before that 2001, I think. Before 2009, the ductility requirement was used as a 0.4. And at that time mostly we use Y-type bars, not N-type. Y-type bars have yielding strength of 400 MPa. Now we have 500 MPa. So that's slightly different. So the standard will be revised. Okay, so you need to understand what is under-reinforced, what is balance section, what is over-reinforced. Balance section is a steel yield at the same time as the concrete. For N-type bars, Ku is equal to 0.545. This is for N-type bars. Okay. because if you change the bar, the yielding strain of the steel will change, so the numbers might slightly change. Okay, so we have two things: under-reinforced, over-reinforced balance section. That is one thing. Another one is a ductility requirements. So then what will happen? Yeah, it will cut on in 5 minutes. Don't worry, if we can't finish it, I will explain that one next week, and I will record the tutorial separately, or I will put the lecture separately recording, and we'll continue with the tutorials. So the singly reinforced sections, or do you want the recording lectures first and do the tutorial for both classes? Which you like? Spending more time with the tutorials or lectures 1, tutorial 1? Which one you like? What I can do is I can put all the lectures before, you watch it, and we will work out the numbers.
Yeah, so lecture and tutorial might be self-continuing. That should be great.
Okay, so we'll go like that, and if you don't finish it, I will put it as a separate. Okay. So remember, this is a double unit, so the content is a little bit more than the normal one. Okay. Okay, so if you have a reinforcement, yes. Okay, now we calculated how much reinforcement we required. So if you look at that, the calculation we had earlier, here, if you want to increase the MU, you need to increase the FT, yeah, or Z, yeah. You need to increase, if you want to increase the MU, that is capacity. If you want to increase the capacity, what you need to increase the FT or Z. You cannot increase Z very much. Okay, you may able to increase a little bit, but not much. So technically you need to increase the FT. What is FT? FT is equal to AST, area of steel, times yielding strength. So if you want to increase the MU, you need to increase the FT. If you want to increase the FT, you need to increase the steel area. So what does that mean? You need to put more and more steel. So if you want to technically to increase the moment capacity, if you want to increase the moment capacity, what will happen? You need to put more and more steel. So the MU will increase with the AST up to that the balance section. After that it will reduce. Okay, your steel will not yield. So the problem is the standard says you cannot go more than 0.36 KU. So if you put more and more steel, KU will increase. So unreinforced section become balance section, and then if you put further, become over reinforced section. We don't want to have those things. On the other side, the KU also cannot go 0.545, so we can't reach the balance section even, because standard says maximum 0.36. So what we do in this case, we will provide some additional reinforcement on the compression zone, so that we have some extra capacity in the compression, so we can increase the steel one as well. So that is called doubly reinforced section. Okay, I'll explain that doubly reinforced section principle in the next class, because it will cut on in less than 1 minute. So but you need to know is, when you need additional moment, you may able to get it through the doubly reinforced sections as well. Okay. Anyway, we'll discuss it tomorrow and we will continue from there. Okay? Is it too fast? Or is it right speed? Or should I too slow?
It's okay, sir.
Okay, okay. If you need